Assalamu alaikum, dear viewers. In this lecture, we will discuss the solution for the problem number 7.30, which says that consider any two continuous function of the generalized coordinates. Mean we have two functions which depend upon the generalized coordinate and momentum. The one of the function is g, which depend upon q, k, and p, k. Q, k, and p, k. Okay, and the second function is h, which depend upon generalized coordinate q, k, and p, k. The Poisson bracket is defined by this g and h. This is the definition of Poisson bracket. You should um, make understand this. G and h is equal to commutator of g and h is equal to sum of k into partial g over partial qk partial h over partial pk, partial g over partial qk, and then partial second term partial h over partial pk minus partial g over partial pk partial h over partial qk. This is the definition of this commutator Poisson brackets. Verify the following property of the Poisson bracket. We have to use prove this by using this definition of the Poisson bracket. The first property dg over dt mean total derivative of g is equal to should be equal to this g h commutator plus partial g over partial d partial g over partial t, and then q dot j should be equal to this p, and pi pj should be equal to 0, and this, and also discuss this result. Where h is the Hamiltonian, if the Poisson bracket of the two quantities vanish, the quantities are said to be commute. If the Poisson bracket means if the two commutator of the two quantities are 0, it means commuting with each other. If the Poisson bracket of the two quantities equal unity, if the Poisson bracket of the two quantities equal the unity, the quantities are said to be canonical conjugate, mean those quantities for which the Poisson bracket is equal to unities, these are called canonical conjugates. Then part E, show that any quantity that does not depend explicitly on the time and the commute with the Hamiltonian is a constant of motion of the system. Okay, means if any quantity that does not depend time and commute with the Hamiltonian. For example, we have q and take its commutation with respect to h, and its commutation for example is equal to 0, so that will be constant of time. I mean that q will be constant of time, does not depend on time. Poisson bracket formalism is of considerable importance in quantum mechanics. Okay, these are the some facts and figures about the problem. So we should start from the part A. Okay, very first part, dg over dt is equal to g and h plus partial g over partial t. So dg over dt is equal to partial g over partial t. Okay, partial g over partial t is written as it plus g and h. Here we should compare this two relation. Okay, here it is g and small h is replaced by capital H. So we will replace the small h with capital H, and here simply we will replace this small h with capital H, and this expression will be modified with that. Okay, and similarly this pk and this whole terms. Okay, if I make centered it so that we can see it. We first write the total time derivative in terms of partial derivative so that we can include the Poisson bracket. Therefore, dg over dt is equal to partial g over partial t plus partial g over partial qk over partial t. We know that g, if g is the function and will depend upon qk, pk, and t. So we can write its total derivative by using calculus. Partial dg over dt is equal to partial g over partial t plus sum of k and partial g over partial qk. Okay, partial g over partial qk over partial t plus partial g over partial pk over partial t. This is the total derivative we can write from the calculus. If we know that g depend upon these variables. Okay, so this is just the total derivatives. You can take help from the mathematics. G depend upon this, so we can write a total derivative like this. Since the canonical momentum are defined as, we know that q dot k is equal to partial h over partial pk and p dot k is equal to minus partial h over partial qk. These are the canonical momentum as we define this. So dg over dt is equal to, okay, is equal to partial g over partial t as 8 plus, in place of summation we will place a summation, partial g over partial qk as 8 and partial qk over partial t. Partial qk over partial t mean this term is q dot. Okay, so you can substitute for this. So this is q dot, so this will be replaced by partial h over partial pk, and similarly this is p dot also. So we will substitute these two terms. This term will this one, and then we will write that partial g over partial qk, this term will be replaced by partial h over partial pk minus partial g over partial pk. Okay, and partial pk over partial t is p dot k, no, yes, sorry, pk dot, which is equal to minus partial h over partial q. So just replace this with this term. Then dg over dt is equal to partial g over partial t plus this whole term is given in the question. If you look back at the question, this is just commutation of q, g and h. Okay, so just you can see back from the question. I think if I center it, this one, you know, you can use this one, g and h, which is equal to this. So just g and h, using this definition we can replace the partial g over partial t plus this whole term as g and capital H. So this will be equal to this dg over dt will be equal to partial g over partial t plus this whole is equal to g and commutator h, as in the given the statement of the question. So this is g and h. So our first properties is proved. Okay, if I erase this, we have to memorize this formula. These formula are important. Q dot k is equal to partial h over partial pk, and similarly p dot k is equal to minus partial h over partial qk. These are the very important formulas as we are using continuously again and again in this chapter exercise. Similarly for part B, in part B we have to prove that in part B we have to prove that q j dot is equal to q and h and pj dot is equal to pj and h. We have to prove these results. So let's go and use some facts. Since from the definition given for the Poisson bracket in the question, Q and H is equal to sum of K partial Q over partial Qi over partial Qk, partial H over partial Pk, minus partial Gi over partial Gk, partial H over partial Qk. And we know that partial Qi over partial Qk is equal to canonical delta. If these two indices are equal, so this will be equal to 1. If this are not equal, mean I is not equal to K, so this will be equals to 0. So just Qi and H is equal to, if these are equal, I is equal to K, so this will be equal to 1 and partial H over partial Pi, because I will be replaced by Q in this expression. When I is equal to Q, so Qi and H is equal to, this will replace partial I is equal to K, so this will become 1 and partial H over partial Pi, and this will be partial Gi, or if I is equal to K, so this terminal goes to partial Gi and partial this terminal goes to 0 because of this term. Okay, so we will left with Qi and H is equal to partial H over partial Pi, which we know that which is equal to Qi dot. And applying the same step again, Pi and H is equal to sum of K partial Pi or partial Qk, partial H or partial Pk, minus partial Pi or partial K. Again we will use some factor, partial Pi or partial Pi and partial Pk, and this is equal to delta Ik. If I is equal to K, this is equal to 1. If I not equal to K, this will be equal to 0. So at this partial Pi, for I is equal to K, so Pi and H, sum of K is partial, when I is equal to K, you know that for I is equal to K, this partial Pi or partial Qk minus this whole term, so when I is equal to K, this term will goes to 0 because of this term, because H does not depend upon Pk, and similarly for minus partial this term for I is equal to K, this term will goes to 1 and partial H or partial Qk will be left as it. So just Q is replaced by I. So you know that this is equal to Pi dot. So this is the result of the part B. For the part C, this is C part. In the C part, we have to prove that Pi, commutator of Pi, Pj should be equal to 0, and in the then Qi, Qj it should be equal to 0. We have to prove this. From the definition of Poisson bracket, we know that Pi, Pj is equal to sum of K partial Qi, partial Qk, partial Pj or partial Pk minus Pi, or as this definition given in the question statement of the question, where we have Q and small h. In this, small h is replaced by P. So where small h is replaced by P as in the given statement of the question. Okay, you can just compare with that equation. So h will be replaced by Pj in the statement. So Pj par Pk minus Pj and partial Pqk. We will use since partial Pi over partial Qk, partial Pi or partial Qk is equal to 0 because P does not depend upon Q, so its derivative will be equal to 0. So partial P, therefore substituting Pi and Pj is equal to this, P does not depend upon Q, so partial P and partial Q will be goes to 0, and similarly partial P and partial Q will go to 0. This both term will goes to 0 and Pi Pj is equal to 0. Repeat the same step. Qi and Qj is equal to, in this case, in the given statement, we will just this H as in the statement will replace with Q. So Qi and Qj will be equal to partial Qi, partial Qk, partial Qj, partial Pk minus partial Qi, partial Pk, and partial Qj, partial Qk. You can just see the statement of the question. Okay, now you can see here that we are given a equation in the statement. This one. Okay, so you can just use this definition to write the commutator of any two operator. If we write two commutator of Qi and Qj, then we can write like this. This H will be replaced by Qi, and similarly sum of this H will be replaced by Qi, and this H will be replaced by Qi. Okay, and then if we write the commutator of Pi and Pj, so we can replace this small h with Pj in the whole expression. H will replace with Pj and this H will replace with Pj. So you can just extend this for the problem part 3, for the part 3 of this one. So we will use that fact, and then we know that partial Qj or partial Pk is equal to 0. We know that Q and P does not depend upon, so this will be 0, and again this term will go to 0, this term will go to 0, because partial Q or partial Pk are independent of each other, so this will go to 0, and this our result will be 0. Now I think so we have a part D also, which says that Qi Pj is equal to delta Ij. If I is equal to j, this should be equal to 1. If I not equal to j, this will be equal to 0. So from the definition of the Poisson bracket Qi Pj, just we will replace that h in the statement with Pj and writing this whole expression. Now we will use some factor. Then partial Qi or partial Qk is equal to delta Ik, and partial Pj or partial Pk is equal to delta Jk. When I will be equal to k, this will be equal to 1, otherwise this will be equal to 0. And the second thing is that partial q or partial pk is equal to 0, partial p or partial qk is equal to 0, so these terms. Therefore by substitution we have qi and pj is equal to delta. Why this is delta? Because partial q and partial q, this will goes to 0, because these are not dependent by using these facts. And this partial qi or partial qk, when I is equal to k, this will be 1 and this will be also 1. So this term can be replaced by delta ij, because for I is equal to j, this will be equal to 1, otherwise this will be equal to 0. So this whole term can be replaced by delta ij, because this is satisfying the property of canonical delta. So delta ij p qi and pj is equal to. And then part E, let G depend upon P and Q does not depend explicitly on time. Let G which depend upon P and Q does not depend on time. Then our total derivative will be equal to dg over dt is equal to partial g over partial t. Mean we can write dg over dt as we have written in the start of the question, which was partial g over partial t plus commutator of g and h. If g and h are commute, so this term will also 0. And the second statement is g does not depend upon time. So when g does not depend upon time, this will go to 0. Then dg over dt will be 0,